Just a reset of energy conservation. So energy conservation is that it basically states that total energy remains constant. Okay, in a closed system, which we know already. Okay, and the other thing that we looked at was what kinds of energies that we were going to specifically use within this class. So within this class, we were looking at kinetic, gravitational, potential, and elastic potential. Now there are many, many more. Like you can have more different kinds of mechanical energies that we're going to use. Like we could have had heat in there. We could have had other types of potential chemical energy and this all kinds of other things like that. But we specifically look at that. So what we're going to be adding in is we're going to add in work done by friction. Is going to be our new idea when we look at that. Okay, so friction never increases. So friction will oppose like kinetic energy, right? So if you think about yourself sliding down a hill or whatever, or riding skiing down a hill, let's say on some skis or something like that, eventually you're going to end up stopping due to the friction of the skis. It might take a while or whatever, but that would happen. Okay, even though you're converting the gravitational energy into kinetic energy, eventually you're going to run out of that energy because it's going to be all dissipated into friction. So we're going to look at some practical examples like that. Or if you drop something out of a high area, it eventually reaches it doesn't keep accelerating anymore, and it reaches a finite velocity because of the friction forces. So that's kind of what we're going to look at a little bit. But before we do that, let's go back and let's do a reset or just kind of an energy problem with drawing. So let's do one that's very common. And let's do somebody maybe skiing down a hill or something like that. Okay, so let's draw a little hill here. I'm going to put myself over here. Okay, so let's say we're going to use a diagram format for our problem today. So let's say we had a ski slope, but on the bottom of the ski slope there's kind of a... Okay, that's supposed to be smooth, that's just me having issues with Tuesday morning here, drawing smooth. Okay, so we'll call this one point A, this one point B, and this one point C, this little rampy thing here. Okay, and we're going to look at, say, somebody skiing on here. All right, they're going to be a ski jumper or whatever. And we're going to say that this drop, this vertical drop here, from the top of point A down to here, let's say this is 12.8 meters. Okay, to this ground level where B is here. Okay. And we'll call this little bump here, let's say that this is only down to that B, that bottom area there. let's call that, that looks like to be about a quarter of that or so. So let's say that's about 3.1 meters. Okay. Okay, this gentleman up here, let's say that, not that we need the mass, but we'll give him mass anyway. Say that this is a 62 kilogram individual. And this individual is standing at the top and has a velocity of 0 meters per second up here. They're just standing at the top with gravitational potential energy. And then we would say, let's ask a couple questions. Calculate the velocity at point B and C. Okay, so we can tell that at point B, he's going to be in a gully, then he's going to lose some energy coming up here to point C, right? Because he's going to give away some energy. So here we have, if we just have our kinetic energy plus our gravitational energy at point A, we know that if we take a look at our top here, there's no velocity, so there's no kinetic energy at the top of the hill. Okay? We know that here at this end of it has some kinetic energy plus some gravitational energy, but we know that it's right at it's right at the bottom of the hill, so that it would be calculated so that there's zero height there. And in here we do have some kinetic energy at point C plus some gravitational energy. Okay, now there's two ways we can find our velocity at C, but we'll do it with a full calculation. So the first thing we can do is to get point B, we can compare point A to point B. So we're going to do point B first, and we'll do that one in blue. So point B. So we'll have point A here and point B here. Okay, so we don't have any kinetic energy at point A, so that's just gravitational energy. Equaling, at point B, we don't have any gravitational energy because it's right along the ground. So this is one like we did before. So this would be like kinetic energy. Okay, so we can put in our values. This is mgh based on these results up here. And this is mv squared over 2. And we can get rid of our m's. Okay, we don't necessarily need that m there that I gave because it's on both sides of our equation. Okay, now you can rearrange it if you want, multiply by 2 and then take the square root and do it that way and plug it all in, or you can put in numbers. Let's put in the numbers first. So we'll go and solve at point B. So here we have our gravitational energy, 9.8 meters per second squared. Or sorry, our gravitational constant, not energy. Our height at point A is 12.8 meters. And that's going to equal our velocity squared over 2. Okay, so we're going to solve for our v. So we're going to multiply by those out and then multiply by 2. So 9.8 times 12.8. Okay, that's 125.44. That's meters squared, second squared equals v squared over 2, times it by 2 to get it into just v squared by itself. So a little bit of math here. That's times by a 2. That's times by a 2, if you're wondering. So this is 250.88. Meters squared, seconds squared. Okay, and then we've got a v squared. Okay, so we're just going to square root it to get our v. Okay, I'm kind of scrunching it in, so I'll just write it on the bottom. Oops. Square root of, why did I change it? 250.88. Okay, so what do we get? We end up getting 15.8 meters per second. Okay, and I'm given basically 3 figures and 2 figures. So we probably should go to 2, but we'll go to 3 just to keep it the same velocity and the meters there. So that would be our bottom, right in the gully there. Okay, now when you get into this part here with C, it has 2 energies here. Now, there's a couple of ways you can do it. You could use the same idea and just subtract this height from the original height, because you would lose some height as you're going back up a little hill. So that's one way to do it. Or you could just sum the total energy at the top and the total energy at the bottom, which is the way we're going to do it, just to show you that both ways are functional. So we're going to take at point C, which I'll do in a different color here. But let's move my brains out of there for a second. Okay, so if we're going to sum point A okay, so we still have just the gravitational energy at point A. But at point C, I've got 2. I've got gravitational and kinetic energy. Okay, so we can do our math in here as well. Like I said, if you wanted to, you could just kind of leave that one out and get the kinetic energy if you subtracted the heights, because it would give you the same result. It's just kind of a shortcut method. But if we do mgh over here and mv squared over here plus mgh over here, again, the similar thing results. If we factored out the m, it's on both sides, right? If we took this and factored out the m, so we don't really need the m of that, because it's in every expression. So we could factor it out and get rid of it. It's a common factor, basically, if you know you're factoring from your grade 10 math, right? So we're taking that out and get rid of it. Just makes it a little bit easier. We cannot do the same with the height because it's a different height. So I'm going to put height at point C there and height at point A so we don't get mixed up. Okay, those are different heights. And we can't do the same thing with G either, because G is not involved in this expression here. So it's not a common factor. It's only a partial common factor for 2. So we can't factor it out when it's not in every expression. So you have to be very careful that you don't cancel something out just because it's in 2 expressions. It has to be in every expression of your equation, just like when you do common factoring in your math class way back in the day. So we're going to put in our results. So we got 9.8 meters per second squared multiplied by that height of A, which was 12.8 meters. And that's going to equal v squared over 2 plus 9.8. You can see why we could have just subtracted the 2, because that's what we're going to end up doing in the math. But I prefer showing it and how it comes about. So this is meters per second squared again, but we're going to multiply by the other height, 3.1 meters. Okay, so again, we're going to work this through. So 9.8 times 12.8 we did before. That was 125.44. This is still there. We're not going to work with that till the end. And this becomes a smaller number, 9.8 times 3.1. That's 30.38. So you can see why subtracting the height would have just gave us a shortcut, because that's what we're doing with the algebra anyway. So we're going to subtract the 30.38 on both sides. Okay, what did somebody say here? Why did we cancel out 2m on the right? Like this one here and this one here, because it's a common factor. Okay, common factor. This m is a common factor, so it could be written like this. Okay, and then take a common factor of m out the front. So this would have been v squared over 2 plus gh. Okay, so when you take it out front and factor it out front, then you cancel it. So we're basically canceling out 1m. Does that make sense to you? So this is why we ended up with this expression, because we did a common factor. Okay, so that's when you're factoring things. Okay, so it's basic, it's algebra thing, right? So I'm not canceling out 2m's, I'm canceling out 1m on each side. Okay? So that's how that worked mathematically. Okay, so let's continue then. All right, so 125.44 subtract 30.38. Okay, when I do that, I get 95.06 on this side. Okay, and that's still meters squared, seconds squared. And what's left on this side, that's gone now, is just the v squared over 2. Okay, and now we're going to get our velocity by multiplying by 2 on both sides. So do that. Get 190.12. Equals v squared. Okay, we're going to square root that now. Okay, when we do that on our calculator, we end up with 13.78 or 8. So you can see it's slightly slower. Slightly slower than what we had for our first one. A couple of meters per second slower. Okay, so that's an example of having two energies, having still some potential energy there. Kind of a ski hill example, very, very common example that we do. Still, we're not dealing with any friction yet. Okay, the algebra that we're using tends to be about, your grade 10 foundational algebra, where you're dealing with multiplying and factoring and canceling and solving. Okay, sometimes you might even have to solve two unknowns with two equations. Okay, but we're not going to get to that part very often. That's something that'll probably show up in your challenging physics that you might take on later after you get out of high school. Okay, generally speaking, in our grade 12 physics, we kind of look at the basic solves of an equation. Okay, sometimes when you're looking at it, you're not looking for 2 to 3 or 4 energy equations. You're just looking for one that you can solve and find a missing variable. This is meters per second. Somebody's asking what what the velocity is, because this, if you think about it, this is meter squared second squared. So when we square root it, it becomes meters per second. So it's not an acceleration, it's a velocity. So velocity is in meters per second, but acceleration, which is what our gravity is meters per second squared. So basically when you're multiplying meters with meters, you get meters squared over second squared. And that's how that works. And why did I put meters per second squared in the last one? Because I made an error. That's why. That's not supposed to be there. Thank you. Should only been meters per second. Sorry, good catch. I'm going to stick you up on my wall. Thanks for the catch there. It should have only been meters per second. Right? They both should have been meters per second. Good question to ask, especially when I make an error like that. Put you on my sticky here. There. Okay. Let's do maybe one with friction in it as well, to kind of show how they work. Now, there's a couple of different kinds we can do with friction. A lot of the time, friction opposes kinetic energy. Okay, it slows things down and it's lost through heat. We could calculate that heat, but we're not going to bother. We're going to just assume that it gets lost out of the system in waste heat. Okay, so we're going to do an example that looks like that. So I'm going to flip the page here, and we're going to do our first example with friction. Okay, so when friction is involved, okay, it takes energy away from, normally from your kinetic energy. Just checking this. Sorry, just let me answer this kid here. There we go. All right, so when friction is involved, we assume the energy is lost as waste heat out of the system. Okay, so it's out of the system. Okay, so we calculate that waste energy using the work equation. Okay, so the work done equation is that work equals force times distance. Right? And then the work is reducing the kinetic energy usually, because you're pushing with kinetic energy and the motion is going to be slower than normal. Okay, so this work reduces energy, kinetic energy, we'll say. Okay, as it's going to turn it into heat. Okay, so let's do an example of, say, air resistance as something falls. Okay. Well, actually, let's just do a sliding example. let's do a ramp. That one's really easy to do. So we'll make a wedge here that represents our ramp. And then up here we have a block. I kind of have to draw, I got to use different tools for that, I guess. I kind of have to draw it on the angle here. Okay, so there's a block sitting on this thing, and we'll say that this block has a center of mass right here. And we're going to say that that mass equals 2.8 kilograms. Okay. And let's say that there's a friction constant of, let's say it's wood on wood, so that's about 2.25. Okay. This is our friction constant. And then from this particular height, right from the center of mass down to ground level, so this is our ground level here. Let's say that this ramp height from that center of mass down to ground level, let's say that this ramp is lifted up to approximately, I don't know, we'll just make up a number. We'll say it's 1.90 meters. And we know that the length of this ramp, because we have to know how long the thing is going to slide and reduce, because with work, we are going to figure out the force, right? That force of friction against it, right? And figure out what it is. Now, typically, to get the force of friction, we need the force that's going this way. So a lot of times, you kind of need to know what this angle is, but I'm just going to give you the force of friction, even though, actually, you know what? Let's do it a little bit simpler. Let's not bother with constant. Let's say the force of friction is a number. Let's say the force of friction is already given to us. Let's say that it's about, well, let's assume that we're not 100%. Let's say 2.8 times 0.25 times 9.8. Let's say that it's about 6 newtons. Well, let's go 5 newtons, 5.0 newtons against the motion. That'll be a little bit easier for us to do. Okay? And then the idea is, what is the velocity at the bottom of the hill or ramp? Okay, so we've got gravitational energy here. We've got work done here. Okay, and we're going to take the length of this. I'm going to guess that I'm just looking at my diagram, that's 1.9, so it looks to be about over 2 times as much. So we'll say that this is, let's say that it's about 4.4 meters. Okay, so that we're going to have work done here, and we're going to have gravitational energy turning into kinetic energy at the bottom. Okay, so this work done is going to be removed from the gravitational energy, even though I said that it comes off the kinetic energy, because we're going to reduce that gravitational energy, so it's going to have less kinetic energy than it should on the bottom. So the total energy at the top is going to be reduced by the work done along the path. Okay? So we're going to have our gravitational energy at the top, and we're going to subtract our work done. So we're going to have some of that energy taken away and lost in heat. And what's not lost in heat is going to get converted into speed or velocity. Okay, so that speed or velocity is going to be reduced by this work done. Okay, and in this case, we won't be able to cancel the mass because there's no mass in the work done formula, right? Like we did last time. We can't do a common factor like we did last time. So we have to put that mass in there. Okay, so gravitational energy, that's mgh. Making the h at this here part and that m. Work done, that's force of friction times distance. Okay, and that's the distance that it slid along the ramp. And kinetic energy is mass times velocity squared over 2. Okay, unlike the last one where we cancel out the m's, there's no m here, so I can't common factor it out. I cannot cancel it this time. Okay, so we're going to solve through that area. So now this actually reduces the velocity on the bottom, but it takes away the potential energy here and takes that potential energy and makes it heat instead of speed. So we're losing that speed that we're going to have on the bottom, or that velocity that we're going to have on the bottom. So let's plug in our numbers. So we've got our mass, what does the heat, this is heat lost. So what happens in this closed system, we could put the heat energy there. So what happens is that this energy, that the friction that's causing that as this block slides down this here ramp, is actually creating an energy that we're not going to calculate, that's lost to the system. It goes into the air. It doesn't go into the speed of the block as it slides down. Only part of the gravitational energy goes into the speed. As it's going down, it speeds up. But the kinetic energy is going to be less than it would be if you had no friction. So it would go a lot faster. So what does that friction cause? It causes heat, which is a type of energy. So we call it waste heat in physics. Does that make sense? So that means that this work done that we're doing here between the top and the bottom, instead of doing, if there was no friction, we just do this one equals that one. But because there's friction, we put and take away the work done by the friction. Okay, so that means this heat is going to reduce, that's why there's a subtraction sign here, the energy as we go down. Okay, so we plug that in, 9.8 here. And the height of the ramp. Okay, so there's our kinetic energy. We're going to subtract the work done by the block as it slides down the complete ramp. So that's 5 newtons times 4.4 meters. And that's going to equal our kinetic energy without a velocity, and we're going to calculate the velocity. So it's 2.8 v squared over 2. Okay, so when we work it out, take our calculators out, you can see that we're going to lose a portion of the energy here. Remember, a Newton meter is the same thing as a kilogram meter squared second squared, which is a joule and a Newton meter. They all work into the energy units. So 2.8 times 9.8 times 1.9 gives us our top energy, 52.136. So we'll just say 52.1, I'll go. And we're going to subtract 5 times 4.4. So that's 22. Okay, good question. Somebody's like, why didn't we cancel the mass out this time? Because there's no mass here. We can't factor it out here. So there's one expression here, two expressions here. There's two expressions. In order to cancel the mass out, we'd have to have a mass here and a mass here. So because there's no mass in the work equation, we can't cancel it out, right? So that's the reason why. Okay. But if we go back to the other one, right? We go back to the other one, there's a mass in both of them, right? Then we can't, that's why we can cancel it out. Here, when we're in this new one here that we're doing, we cannot because there's no mass there. Okay? Good question to ask when we're doing the math part. Okay, so then 5.0 times 4.4 is 22. So you can see that we're reducing by about 22 joules of energy. Now this would be joules here, and this would be joules as well. And then 1.4 when we divide 2.8 by 2. Okay. All right, so then when we work it out, we got 30.1 on the left side. Now this is joules, but we don't need to worry about units because when we take joules and divide by kilograms, we're going to get meters squared second squared, and then we're going to get meters per second again, as long as we're using kilograms as our unit here. Okay, and then this is 1.4 v squared. So I'm going to divide out the 1.4 because it's multiplied this time. So divide by 1.4, 30.1 divided by 1.4. So that's 21.5 equals v squared. Now this would be meters squared second squared, and then we would square root it to get our final answer, 4.6 meters per second. Okay, so there's a more complex idea of losing some of our energy as it slides down a ramp because it's rubbing against, the two surfaces are rubbing against each other, causing friction, which would basically warm up and become waste heat. Okay, we could calculate the heat if we knew some parameters about the heat, but that's beyond the scope of what we do here in Physics 30. We just look at the losing it to the atmosphere or to the air. And what would happen if you did this lab where you're sliding things down and you're calculating the velocity at the end, that would happen. You would actually lose energy because of the friction. Sometimes if you don't lift the ramp up high enough, it doesn't even move because the friction just holds it there. Okay, so that's an example of using friction in a ramp problem. Now I think what I'm going to do is I'm going to stick to giving you the frictional force because I'm not really interested in the geometry math, because if we do the constant of friction here, we need the angle down here, and then we'd have to do all kinds of geometry, and that just adds complexity in the math, which I'm not really worried about. I want more the complexity to be in our physics solve, not our math solve. I want to keep the math in that grade 10 level. All right, so one more thing for today, and we'll call it a day. So that's an example of using energy conservation when friction is involved a little bit. Okay. Now we haven't used one with an elastic energy, but we'll kind of save that for next day. Okay, and we'll just summarize this. Okay, so just what's going on here to keep it fresh in our mind. So in this ramp problem, the gravitational energy transforms into kinetic energy at the bottom. And as it travels, period. As it travels, as I guess we should be more specific, as the block travels, down the ramp, friction is created. Okay. Why don't we multiply 2.8 by 2 to cancel it out at division? So you see here. We can multiply both sides by 2 if you wanted to. So I just simplified 2.8 divided by 2 to make it quicker. But if you wanted to, you could have multiplied by 2. This would have been 60.2 then, equals 2.8 v squared, and then you would have got the same answer. Does that make sense? Somebody's asking me in chat that why you could do it both ways. You could do the divide first, or you could multiply then divide. Okay? Okay, so as the block travels down the ramp, the friction is created and then lost as heat to outside the system. Thus, the reason the work is subtracted. From our energy. Okay, so that's why we're subtracting. Okay, so we're looking at the explanation to what's happening here. Sliding down, and that sliding down is going to be slower than it originally would be. So thus, the velocity becomes slower than if there were no friction. Now, some physics guys, teachers, don't really put the friction part in there. I do, because I know from personal experience that there's always friction involved in stuff. And if you end up doing a lab, you never ever get the exact velocity that you're thinking of. Even when we do our momentum lab later in the unit, it's going to be slower than what we would expect because of friction and things like that. Anyways, I'm going to stop there at this point today. And we'll get into a couple more things about energy conservation in our next class on Wednesday. So that will be our stopping point for today. And we'll see everybody on Wednesday, hopefully.